heard that saying? What does that mean, to not be able to see the forest for the trees? What it means is if you're in the forest, you're surrounded by these huge tall trees, and all you can see is the few things in front of you, the few trees in front of you, so forth. You can't see the whole forest because you're caught up in this one small part of it. Well, that's what that is meaning you get so caught up in the details of the situation that you can't see the big picture. And that's what happens sometimes in these problems. You get going through stuff. Sometimes you've got to step back and you've got to think about, okay, now what do these equations mean? What am I trying to accomplish? And that's what should guide you as to what you do. Okay? So right here, all right, so yeah, I know I'm supposed to kind of do a derivative and set equals 0. Hopefully you understand that that's when this equation would be at its peak. And then when I get this, what does that mean? What's that number mean? That's right. All that tells you is that's how far out from where you kick the football when it hits its maximum. So that didn't answer the question about how high it goes, right? So what do you need to do? Plug it back into the original to get y, because what you want to know is how high the football was that time. Or that. That's not really a time. That 45 is not a time. That's the horizontal distance when it hits its peak. And then it says, where does it land? Well, what happens when it lands? Not x equals 0. You want to know what x is when y is 0. So so you go back to the original and put a 0 in for y, and then find that x value. That's how far it traveled. So where was it when it landed? That's, well, since it's a parabola, it's double that number, right? I mean, because this is going to be symmetrical, so it's actually 91 point whatever. Okay, but the reason I went into this one here is I wanted to talk a little bit about 21, the part that I had you skip. On 21a, they said we're going to rearrange the 19 equation to talk about the range of the football, how far it traveled. Because I think you might have done 21b, but I'm not sure you really understood what it is you were doing, and there's a lot in this problem that's kind of interesting. And so the range would be this. The more interesting question here, yeah, it's interesting to see how high the football went. But a more interesting question might be, what could we do in this scenario with initial velocity and m as slope that would give us the farthest kick of the football or whatever object we're throwing? So how about maximizing the horizontal distance, right? That's what we might be interested in doing. Or if we had a shot putter throwing the shot, right? We might be interested in what is the maximum we could throw. So that would be the x variable, right? So if we want to maximize x, we would need to write this equation as x equals, right? Now, when the shot put, the maximum distance of the shot put is when it's where? I mean, we measure it from where we throw it to where it lands, which means what? Y is 0. So if we're going to want to solve this equation for its maximum distance, we're going to put a 0 right there, and then we're going to want to solve this for x. Okay, so that's the part I had you skip in 21a, was take this equation, put a 0 in for y, and solve it for x, because x is its horizontal distance, and 0 would be when it lands on the ground. So I'm going to go ahead and do that. So we would get 0 equals mx minus g over 2. Did I do that right, or is that backwards? That's right. And then 1 plus m squared x squared, right? So I'm going to add this over to the other side, so I get g over 2v squared. Well, wait, first of all, I would factor out an x, right? And I have g over 2v squared, and v is the initial velocity, right? 1 plus m squared x, right? That's if I factored out an x, right? So now either x is 0, well, of course, that's at the beginning, right? There's 2 times when the shot puts on the ground. Beginning and at the end, right? And so so either that's 0 or this is 0. So now I'm going to just take the one in parentheses and set that equal to 0. Okay? So set this equal to 0, add that over to the other side, so I'd have g over 2v squared, 1 plus m squared times x equals m, right? So I just took this and set it equal to 0. I added that over to the other side and I have this. So now I want to get x by itself. So I need to divide both of these over here, right? So when I divide those over here, when I divide this over there, wouldn't it just be reciprocal? So I have this And then when I divide this over here, I'd have m over 1 plus m squared. That make sense? And isn't that the equation that they give you in number 21? Okay, and they, instead of calling it x, they call it r for range. The range, you know, how far it travels, the distance, or whatever you want to call it. So this would be, so that's where that equation came from in number 21. Okay? All right. And so now, if we go back. Okay, so if we take that equation, so think about what we're trying to say here. So we're going to throw the shot put, and not really throw it, I guess. We put it. But V sub 0, so what are the things that are going to determine how far the shot put goes? Well, one is going to be gravity. Okay, so that's constant. That wouldn't change. One is going to be the initial velocity that we throw it at, right? So, you know, Luke McNitt might have one initial velocity when he throws it. Mandy might have another, right? When she's going to do a little shot put this year. Okay? You know what I mean? But that would vary from person to person. So what the initial velocity you put on the ball when you throw it. And then what was M again? Slope, which usually when you're talking about throwing the shot put, you wouldn't really talk about slope. You talk about the launch angle, right? What angle you would launch at. That's really what M is. And in the problem, they told you to let M equal 1, right? What kind of angle would M equal 1 be? That's 45 degrees, right? A slope of 1 is 45 degrees. So we were working with 45-degree angle. All right. So what they said to do in this problem is let's let G, which is stay constant, which it is constant, and let V sub 0 stay constant. Okay. So we got one person throwing the shot, and they always throw it with the same initial velocity, right? Which isn't probably true. I mean, some throws you probably throw it a little harder than others, whatever. But let's say that you're going to throw it with the same initial velocity every time. So this is just going to stay constant. So this is just a fraction that's just constant setting out here in front. M is going to be variable, so we're going to have various launch angles. And we want to see which launch angle will give us our max distance. Okay? All right, so we're already at step 3 on the steps, right? We already have our variable in our equation in terms of only one variable. M's the only thing that's changing here. This is all constant. So we're ready to do what now? To find the max. Okay, now there's a huge pause there of what we're supposed to do, and that worries me. Okay, that worries me. So let's back up here just a second. So when we're going to do because you're getting so caught up in forest for the trees, you're getting so caught up in this other stuff that we're forgetting what is the basic thing we're trying to do here. Go back to chapter 2. Okay, go back to chapter 2 when I would give you a function, and I would say f of x equals this, from 0 to 2. Find the absolute max of that. Well, there are 3 places the absolute max output of that function could be. Where are they? Endpoints, when the derivative is 0, derivative is undefined, right? So here we're at step 3. I've given you a function in terms of one variable, okay? And we want to maximize or minimize that. Now, where could that be? Well, here would be an example where the minimum would be right here, where the derivative is 0, right? Or if I change a function to be this, where's the minimum? At an endpoint. Where's the maximum on this one? Derivative 0. What if this function came up and did this? Now where's the maximum? Where the derivative is undefined, right? Or what if this function actually came up like this? Now where's the maximum? An endpoint. See? So that's what we're doing. When we have a function, when we see a graph, it's easier, but when we have a function, we want to know where its max is or its minimum. There are 3 places it can be. It can be when its derivative is 0, when its derivative is undefined, and at the endpoint. So when I ask you, okay, when I get to this problem, and I say, here's an equation, here's a function for how far the thing goes, and I say, what do we need to do to find the max of that? Derivative, I mean, it should just come right, because there's only 3 places where it can be, and 2 of them involve the derivative. Right? So, I mean, so as soon as you say, hey, we got a function in terms of one variable, where's its max at? What do we need to do next? Derivative. There you go. That's what we want to think. Okay, there shouldn't be any hesitation about what to do. All right, so we need to do the derivative. Now, this is just a constant. It's just setting out in front. So we'll just leave it out in front, and we'll do the derivative of this. Now, we're doing the derivative with respect to m. M is our input variable. So we're doing dr dm. More and more, it's going to be important to think of this notation. Now, yeah, we'll call it R prime, that's fine, but we're doing dr dm. We're doing the derivative of R with respect to m. All right, well, how are you going to do that derivative? You need a quotient rule. Now, you could use your calculator, too. And the calculator, you could actually put in V and G, because when you do a derivative, at the bottom, you have to put the dx or whatever, right? So when you're on your Inspire calculator, you could do this derivative, and on the bottom, you put m, dm, right? Doing the derivative with respect to m, and it would treat m as a variable, and it would treat these as constant. You could literally do this derivative on your calculator. But here's what I did. I went ahead and did the quotient rule. I simplified it a little bit, and I got that. And then, of course, that stuff at the beginning. Okay? So there's my derivative. And I'm going to set that equal to 0. Now, will that ever be 0? What's the only way that would be 0? If the initial velocity is 0, which means you didn't even throw it. So that's not going to be a maximum. Right? Okay? And so m is our variable. And so what's the only way this fraction will be 0? Top is 0. And when will that be 0? When m is 1 or -1, but then we'd have to throw it like that, and we're not going to do that either, right? That's not going to be, okay? So we can ignore that, all right? So basically when m is 1, we can ignore that negative. So m is 1, which is what? That's a 45-degree launch. So what we think the max is going to be is at 45, but have we discovered everything? No, we haven't talked about endpoints. So our endpoints would be what's the littlest m could be. Well, the littlest slope, you could throw it out, would be a launch angle of 0, which again is not going to go anywhere. And what's the biggest m could be? Well, careful. 90 degrees straight up, but what's m? That's your slope. That's infinite, right? That's undefined. But again, so this would be a good one. And I know some of you are getting hung up on endpoints. And what exactly is the endpoint and so forth. Usually they're not that big a factor. You have to discuss them. But in this case, I think I would just say, have a quick sentence that says, the littlest m could be would be 0, which would be, you would not throw the ball up at all, so it would have no distance, or you could throw the ball straight up and it would have no distance, so those are not maximums. I mean, just a sentence like that could discuss the endpoints pretty easily on this one. So that leaves you just this one candidate. So you could do a quick little number line, R prime, put 1 on it, pick some numbers over here, like 0.5 or something, and a number over here, and see that it does that. And sure enough, that's going to be enough. Okay, that'd be one option. I did notice in the answer book, and some of you might like this as an option to use. They said, on one of theirs, they used the second derivative. And I thought, well, that's interesting. They found that R prime was 0. I don't know if it was on this problem or another one. But they found R prime is 0, let's say at m equals 1. And that was their only candidate. I said, if you only have one candidate, do a number line. Right? Show that it's always increasing before and always decreasing after, and then that's a max. Okay, we're going to have a handful of problems over the next couple of days where your equations are pretty simple. Like you can look at the equation, it's just a parabola. It's an upside-down parabola. Well, you can just say, hey, the equation's an upside-down parabola. Here's what it looks. The max has to be. I mean, you know what I mean? That could be enough justification when it's simple like that. But let's think about this a minute. When we learned about the chart, we learned that if the slope is 0, one of 3 things is happening. What? Max, min, flat spot. Now this is something called the second derivative test. What's a second derivative tell you about a function? Concavity, right? What's a concavity on a minimum? Concave up. The maximum? Concave down. On this one? There isn't any concavities at that flat spot. It's changing concavity. It's an inflection point. So what's our double prime on this one? 0, negative, positive. So another way to test that something's a maximum, if you only have one candidate, another thing you could do, instead of doing a number line, is you could do the second derivative and plug that number in. And actually just do the second derivative with your calculator. It's pretty easy. Do the second derivative, plug in the 1, and if you get a positive, it's concave up, be a minimum. If it's negative, it's concave down, be a maximum. If you get 0, then it's neither, but that's usually. So that's another way you could show, when you only have one candidate, you can show that it's a max or min. So I talked about doing a number line to do that, but also you could do this. Now, if you have multiple candidates, that's when the list of candidates comes in handy. All right, So let's talk about this. So this turns out to be a max when M is 1, which is 45 degrees. Now, do we have any shot putters in here? Sam, you used to throw a shot? A little bit? Ever? Back in the day?
Back in the day.
Mandy, I know.
You and Jordan.
Now, so, well, okay, we had a couple in second block. And I asked Dayton, I said, what does Coach Larson say when he tells you to throw the shot? Does he tell you to throw it at 45 degrees? And he said, no, he tells about 42 degrees. So, yeah, big difference. I mean, how could you, oh, shoot, I threw that one at 43 degrees. You know, but, I mean, why would he tell him 42 degrees and not 45 degrees?
Because with this, it's not accounting for like wind and different things like that.
Not quite, because the shot put the wind isn't going to affect it.
Because in reality, the shot put is like 4 or 5 feet above the ground.
That's right. In this picture right here, in the problem we did, we're starting from the ground and going to the ground. And so what that is saying is that the max distance would be if this angle right back here is 45. Where are you really throwing it from? Like maybe there, right? And what would be the tangent line there? Well, it would be a little less, wouldn't it? As you go up that parabola, it's a little bit less. So it makes perfect sense. So maybe Mr. Larson knows more calculus than he's letting up. Or maybe he read it in something, which is probably more likely. And actually, I've talked with him about this. And so when he says 42, it actually wouldn't always be just 42, right? It would depend on what? How tall you are. The taller you are, a little bit flatter on your throw. The shorter you are, a little bit higher of a launch angle. Now, back to the original equation and what we were talking about earlier. Coach Larson probably doesn't spend a whole lot of time worrying about whether it's 42 degrees or 43 degrees or 44 degrees, because in the equation there are 3 different things that matter. One is gravity, which you can't change. One is your launch angle, which you could affect, and one is initial velocity. Which one's the most important?
Velocity.
Initial velocity. So if Coach Larson has things to work on, he's going to say improve your initial velocity. Get in the weight room. Technique, right? Your technique so that you get your weight behind it, you know, and as much force as you can so you can get the initial velocity. So that's the thing you're going to work on most of the time. But that angle could be important. For example, let's take Olympic caliber athletes, right? Take the top 2 or 3 shot putters in the world. And they're wanting to, because now it could be a matter of inches that determines a gold medal at the Olympics. So in their training, through various training techniques and possibly pharmaceutical substances, they have, you know, maybe maxed out what their initial velocity is. They're as big and strong and whatever they're going to get. Okay, and so they've maxed out that what they could do with initial velocity, and their technique's pretty good. So that's where they would use video and high-def video and slow-motion video to look at their launch angles and possibly small changes and corrections in getting that launch angle just so could make the difference at that elite level. You know, but at the high school level, you're probably not, you know, making a huge difference or deal about that. You know, you're trying to get consistent where you need to be. But you know, I was telling the other class about the 2 hardest classes I took in college. And, you know, I took a lot of math classes and advanced, you know, abstract algebra and you know, some crazy stuff that was not very easy. But the 2 hardest classes I took were both for my coaching endorsement. And you don't even need a coaching endorsement to go into coaching. But I took these 2. One was anatomy. And at UNL, they only had one anatomy class. And it was taught by this crazy guy named Dr. Johnson. Ask Mr. Limbach sometime about Dr. Johnson at UNL. Mr. Limbach and I didn't know each other, but we think we might have been in the anatomy class at the same time. He had an eye condition, so he had to wear sunglasses all the time. So he always had these dark sunglasses, which added to kind of creepy factor. And he was tough. I mean, never smiled. Always had these sunglasses. And we worked on actual cadavers in the anatomy lab. And all the pre-meds and everybody took it. I mean, it was, and if you transferred in from another school, like in pre-med or something, and had anatomy in your transcript, it didn't count. You had to take anatomy from Dr. Jones. And I would just get my coaching endorsement. I mean, with these pre-med people, a lot of them were taken for the second time because nobody got an A the first time. I mean, it was hard. I mean, so I took my D plus and move that along because it was just right. Oh, it was hard. Lowest grade I got in
Don't scare
college.
me.
It was hard.
Is that teacher still there?
It was. I doubt it. Mr. Lemma, he probably.
That would make my decision.
Yeah, that was. No, it was. It was hard. Have you ever seen the movie Gross Anatomy?
Let's
Kind of an
watch
older
it.
movie. But it's kind of very much like that. There are three men, very tough men students studying all that long kind of stuff. Anyway, the other course was the one like this. It was called biomechanics for coaching. It was basically physiology, kinesiology, and it was actually taught also by this Dr. Johnson, and it was 1 credit hour. I'd never worked harder in a class my whole college career for this 1 credit hour biomechanics course. But this is what we did. I mean, divers and launch angles for like track and field and all these various sports, and studying. It was like physics. It was like physics on steroids and all this stuff about the science. You've seen the TV show Sports Science on ESPN and stuff where they go through all that. That's what it was, basically. Okay, learning a lot of that stuff. It was a good class, but it was just hard. But it was a lot of these kinds of things, a lot of mathematics and so forth. Okay, so that's a good problem. I think that's an interesting problem. All right, let's look at number 20. Which was it? 27? Real quick, let's look at number 27. Okay, 27 was again very much like the other kind of box kind of problems that we have. You were going to make a skeleton of a box with wire. You had 100 centimeters of wire. So the volume of the box is still this x squared y. But the key is you got to be able to come up with this equation. Okay, there's 100 centimeters of wire. If you look at your picture, there's wire here, here. There's 4 places where the wire's y units long. So that'd be 4y. And then there's 1, 2, 3, 4 down here, and 1, 2, 3, 4 pieces of wire up here that would be x. So 4 and 4 is 8. So 8x plus 4y equals 100. Okay, so you need that information there to then solve for y, substitute in there so you have just one variable, and now we have our volume equation. In terms of one variable, we're trying to find the maximum volume. So what do? Still too big a pause. We do the derivative. Okay, do the derivative, because one of the places we want to look is where the derivative equals 0. Now, I didn't put derivative undefined. Derivative's never undefined on that last problem we did. Derivative's never undefined on this one either. Okay, so we should have that on there. Okay, the smallest. Now, on many of these kind of box and rectangle kind of problems, the endpoints are, what's the littlest x could be? Well, it could be 0. Now, you probably heard on the video, we were talking in the other class, when I said on that problem with the shipping, it said there was a long side. Remember that part of the video, if you were awake? Where it said the long side was x, and then I asked the question in the class, what's the smallest x could be? And we said 0. The smallest could be a 0, and I think somebody spoke up and said, well, no, it couldn't be 0 because that wouldn't be the long side anymore. So we kind of had to figure out, well, what would be the smallest it could be and still be the long side? That's a good technicality and something that's great to think about, and we might have to consider. Probably on the ones we do, the vast majority of the ones we do, that won't be really an issue. You're typically safe saying, okay, what's the littlest x could be, especially in these kind of rectangle box ones. Littlest x could be 0. And what's the biggest it could be? Well, the biggest it could be would be usually if the other one is 0, right? The biggest x could be is if we used all our wire for x and none of it for y. So if y is 0, we would have 8x equals 100. We divide by 8, and then that'd be 12 and a half. So on this one, I think it would be appropriate to do that as your input. Okay, but again, if you don't have one of the dimensions, you're not going to have any volume. So when you do your list of candidates, that's going to show up. So our list of candidates, we put our 0 into our volume equation, we put our 12.5 into our volume equation, and we get 0 for each of those. And then we put our 8 1/3 or 25 thirds in, and we get whatever that is, and that's our math. And then I think it wanted the dimensions, so if x is 8 1/3, you put that right back into here to get y. I think it also came out 8 1/3, right? And so it turned out to be a cube. So it was 8 1/3 by 8 1/3 by 8 1/3 would be your dimensions. Okay? Now, in part B, then it asked for the surface area. And somebody in the other class asked, are we going to have to know the surface area? Well, yeah, there's not really a formula for surface area of a box. It's just what? It's just the area of all the faces. So, I mean, I suppose if I gave you that problem and said something about surface area, I might just say in there, well, it's the surface of all the faces. Now, if it's a cylinder, it's a little bit harder, and I might give you that formula. But what would be the area of this face right here? That would be, how much? It would be x times y. And how many faces are like that? There's 4 of them. So your area would be 4xy plus, and then you'd have this face on top and bottom.
2x squared.
And yeah, and the area of that is x squared, and there's 2 of those, so you'd have 2x squared. So that would be, so the only thing that would change in this problem here would be that. This would still be true. You still have this much wire. So for part B, you've got this equation. You solve it for y. You substitute that in there. And then you've got your area equation. You do the derivative, set it equals 0. I think it came out of cube also, though, didn't it? I mean, I think it ended up coming out the same. Okay, but the process, going through the process is the key. All right. Let's move on. We are going to now, on the business packet. Everybody grab the business packet. Let's talk about one more thing there, and then we'll talk about this next section. And because I want to move into that, I mean, we could work a couple more days on optimization, then work for a couple days on related rates, but I think it's important to move into the next thing, get that, and then spend a day or two where we're just working on some of all the different types. Because on the quiz, you're going to have to identify, is this a max-min problem, is this a related rate, which we're going to talk about today, parametric equation. I mean, you gotta be able to understand those differences. So we'll continue to work on those. Now in the business packet, did I hand those out? Everybody's got one? Okay. So in the business packet, and I've got this answer sheet to the business packet with it all worked out, and on the website, in the files section down below on our class website where the videos are, I've got this answer sheet as a PDF there. So when we're working on the packet, if you're working at home, you can pull that up and look things up, okay? All right, so turn to page 216 on that packet. Page 216 on that packet. And there's a table here of these business terms. And so you'll want to refer to this. This one up here we won't mess with. Okay? So when we're doing a business type problem, those of you that might go into a business field and you'll have to take maybe applied calculus or business calculus, you'll do a lot of these kinds of things. All right? So usually they deal with your produce or sell so many units. A lot of times in the problems, those are the same thing. They just assume whatever you produce, you'll sell. All right? So X is typically the number of units you produce or sell. Little p is the price per unit. And a lot of times that changes. Okay, in other words, and oftentimes this p is called the demand. I think in some of your examples it's called that. It's called the demand function. The price per unit is often called the demand function because the more demand, the higher price you can charge. So the more that you sell, the higher the price could be. Okay? Actually, it could be the fewer you sell, because the fewer you sell, maybe the more demand there is. Okay, or the fewer you produce. I remember a few years ago. It's been a few years now. The Wii used to be really hard to get. Anybody remember that? I mean, I thought it was only a year or two ago. I mean, there was a number of years ago where you couldn't find them. You know, you couldn't buy one. It was months ahead, you know. And they kind of undersold it. There was very high demand for it. So they could have raised the price. They probably did have the price higher than it needed to be. I don't know that that's true now. But so the price per unit is sometimes called the demand. So the price per unit is not always just a constant. It will vary based on X. So a lot of times the price, the little p, is an equation. is actually an equation with X in it. Okay? Revenue. Revenue is the total money you bring in from selling your product. So it is your number of units, X, times your price per unit. And again, your price per unit is sometimes an equation. So, all right, that's your total revenue. And then there's the cost of producing those units. So that'd be your labor cost and your materials cost and your overhead for maybe rent on a building or whatever, all the different costs associated with producing something. And then your profit is your revenue minus your cost. And that's the important equation we need usually in these problems. Most of the problems are finding a max profit. So you have to write a profit equation, which means you need the revenue minus the cost. To get the revenue, you often have to take the number of units times the price per unit, right? So you kind of build your equation from this information right here. Another function that you sometimes need is called C bar, C with a bar over it, which is just your average cost per unit. So that takes your total cost, which is the C function that they might give you, and divided by X, which is the number of units you produce. And that's called the average cost per unit, or the C bar. Okay, and then these three over here, we probably will talk more about these in the coming days. Marginal revenue, marginal cost, and marginal profit are the derivatives of those equations of revenue, profit, and cost. So that'd be like R prime, P prime, and C. Okay, and we'll get into those. Okay, so you're going to be doing some work on these in this packet, and again, they're just going to be max min kind of problems. Find the minimum cost, find the max profit. And setting them up, you will refer to kind of the information in this paper. Okay? All right. So that's kind of it for max-min problems. The rest of the week we'll be, throwing in some of these as part of our homework and working on it. All right. Next thing we want to do is this. So you want to get your notes out, and we're going to do a couple of examples here. Yes? Okay, this would be section 4.5. So 4.4 was parametric equations. 4.3 was optimization, max min problem. And 4.5 is this thing called related rates. Okay, and we're going to work a couple of examples. And in the course of working these examples, we'll kind of come up with a set of steps to follow, kind of like we did with optimization. Okay. If it helps you to have these steps written down. Now, what's a related rate? Well, just like the name said, it involves rates. So it almost always involves some time period. So it involves motion, usually. Usually it involves motion. For example, there's a problem we'll do later on about blowing up a balloon. Well, if you would blow up a balloon, let's say it is a perfect circle. Let's just say it's a circle as you blow up a balloon. There are several different changing quantities there. What's changing as that balloon blows up? The volume is changing. So there would be a rate there, liters per second, or gallons per second, or cubic centimeters per second, right? That would be a rate. What else would be changing?
Surface area.
Surface area of the balloon would be changing. Right? So that would be like a derivative. These would be derivatives, right? Because they'd be rates. So that V would be like V prime, right? dV dt, right? Because it would be with respect to time. Or dA dt, A prime. The surface area would be changing. What else? Yeah, there'd be all kinds of other physical things. The pressure, would change, right? Because that's related to volume. I'm thinking just a circle. What about the radius of the balloon? The radius would be lengthened, right? Or the diameter, those would be basically the same. So the radius would change. That'd be R prime, dr dt. So, and they're all related. That's the name related rates. As the balloon increases, as its volume increases, its rate. So if it's increasing faster, the volume would be increasing faster. The radius would be increasing faster. Right? As one changes, the other would change accordingly. So they're related rates. So simple example right there. Okay, if one of your homework problems is like this. If I click right here, and drag, what's happening? The area of the rectangle is increasing. So is the perimeter. So is the length. So is the width, right? And so the length might be increasing at a certain rate. But I might be, if I was dragging it mostly this way, the length is growing a lot faster than the height or the width, right? And so they wouldn't necessarily be increasing at the same rate. Or if I pulled this way, the width is increasing slower than the height might be, right? And then, so a question might be, how fast is the area? If I know how fast the width is changing, how fast is the area changing? And so forth and so on. So those are the kind of questions we're going to have. So it's going to sound the question will be, some people always ask me, was this an optimization? Is this a max min? Well, just read the question. If a max min problem is asking for the max or the min, the largest, what's the largest area? What's the minimum cost? That kind of stuff. A question like this is going to be how fast? How fast is the shadow moving? How fast is the area increasing? How fast, you know what I mean? It's a totally different question. Totally different question. So what they have in common is a derivative is going to be involved somehow because it involves a rate. It involves a rate. Okay, so our first problem that we're going to look at is this problem right here. Oops. All right. A 6-meter ladder is against the wall. So when you're given a problem in this assignment, you would be given the blue box, basically. Picture would be up for you to draw. A 6-meter ladder is against a wall. If its bottom is pulled or pushed at a constant 1/2 meter per second, let's say pulled, we're gonna pull the bottom of the ladder out from the wall. So if the bottom is pulled or pushed at a constant 1/2 meter per second, how fast is the ladder top sliding when it reaches 5, 3, or 1 meter up the wall? Well, usually in a problem we would only do one at a time. So let's just do. Oops. So let's just do one question at a time here. So we'll just ignore this. All right. So that's basically our question. All right. So it's kind of cool that they have the picture drawn here for us and everything. But normally in your problems you're not going to. But hopefully this helps us to understand the situation a bit. So what we have is, oops. Okay. So the ladder. Okay, so the ladder is up against the wall, and we are now going to pull the bottom of the ladder out at a constant 1/2 meter per second. All right, here we go. Now, what do you notice about the top of the ladder as it's sliding? It's getting faster and faster, isn't it? So the bottom of the ladder is sliding out at a constant. If you pay careful attention to that, it is a constant. If you just watch this part right here, that's moving at a constant speed as it goes in or it comes out. Okay, but this is slow and then getting faster and faster and faster. So there is not one answer for how fast is the top of the ladder sliding. That's why the question asks 3 different ones. How fast is it sliding when it's 5 meters up the wall? How fast is it sliding when it's down here? How fast is it sliding when it's down here, right? Those are going to be 3 different answers, all right? Now, we would typically only do one. Let's do this one when it's 5 meters. We'll do that one, okay, which would be when it's right there, okay? So what would this look like? Well, let's set it up as if we didn't know what this picture looked like, and we were just going to do it here. So we'll just put it in there. So first step is to identify the things that are in the problem and what they're asking you for, and to draw a picture with labels. Now, I think in my notes I have that as 2 different steps. It doesn't really matter what order you do that. In this one, I think I would draw the picture first. So I have a ladder. Here we go, sliding up the wall. Turn my video. Richard, turn my video on here. Be more excited. All right, here we go. So I got a ladder sliding down the wall. Now, what I like to do if I've got motion going on in these problems is to put arrows in there to show the motion. So what I have is the ladder is sliding out, which means the top of the ladder is sliding down. Okay? Now, I want to label this picture. Now, I know you already saw the other ones. That's a little bit of cheating. But this is probably the biggest mistake that we make in these problems is how do we label the information that's in the problem and put it in to the picture. If we don't screw this up, then we should be great. So tell me what I could label here. I can put a 6 here. Okay. Put a 5 right here. Stop. Okay, we're already wrong. Which is fine. I knew you'd be wrong, and I wanted you to be wrong to prove a point. Okay? One of those is right, and one of those is wrong. The 5 is wrong. Why? In the picture, it was a Y. Well, actually, it was a Y and a 5. The 5 is wrong. The 5 should be a Y. How come? Say it again, John. John, say that or Zach? Who said it? Zach.
We're looking for the rate at which it's falling down. Is that 5 years?
Okay. So Y will be 5 at some point in this problem. Okay, but it's changing. That as the ladder falls, Y is changing, right? Now, why can we put the 6 in there? Because the ladder height never changes. Okay, so this is very, very critical. When you label your diagram, you have to put numbers in for those things that are constant throughout the problem. And you have to put variables in for those things that are changing throughout the problem. That's why they're called variables, because they vary. Okay? So a 6 goes in for the ladder because that will not vary. But this, as the ladder falls, is going to be changing. So we need to label that with something. We could use an A, a B, a C, a Y, whatever. Okay? Call it Y. And then over here, I want to write Y equals 5 because later, I am going to put a 5 in for Y. But I can't plug it in until later. That's very, very key. All right. Because Y is changing. All right. What about this side here? That. Now, okay. Zach said 1/2. It did say it was constant, right? It said the ladder was sliding out at a constant 1/2. But that's a derivative. That's a rate, right? These are distances. So this is a length. This is meters. This is meters. This is meters. And that was meters per second. So what did you call that 1/2? That's x prime. That's exactly right. dx dt, which we'll get to in a minute. So I'm going to label this x. Again, it wouldn't have to be x. It could be something else. But they called it x in the picture. But again, that's a changing amount. Changing amount. So we need to label it. All right. So the 1/2. So if we go back to the problem, what else did they give us? They told us 6. I got that in my picture. The 5, which I'm going to put in later. And they told me this is 1/2. This is increasing at 1/2 meter per second. And so that is x prime. Now, I'm going to call that dx dt. But it's also x prime. And that is 1/2. dx dt or x prime is the same thing. But notice it's with respect to t. See, some of you are already thinking, x prime. I thought we didn't do x prime. Well, we didn't do x prime when what? When we were doing the derivative with respect to x. Because if we're doing the derivative with respect to x, then x prime would be a dx dx, which is just 1, right? The derivative of x would just be 1. But here we're doing the derivative with respect to t. X and y are both changing quantities in terms of time. So the derivative of x is x prime, dx dt. Okay, and that's 1/2. Now, another thing we got to be careful of is that a negative 1/2 or a positive 1/2? Why positive? Because x is increase. Think of the chart. X is increasing. What's X prime? Positive, right? What's Y doing? Y is decreasing. The ladder's falling down. If Y is decreasing, what's Y prime? We would expect our answer to be negative, right? Isn't that what we're trying to find is Y prime? Okay, so I think we ought to write dy dt or Y prime question mark. So the first two steps of one of these problems is draw and label a diagram. Anything that's constant, you can go ahead throughout the problem, go ahead and put in that number if it's not going to change throughout the whole problem. And anything that is going to change, you need to label with some variable. Okay? In this case, X and Y. Then write down the given information. They told us that we want to know how fast the ladder is sliding when Y is 5. They told us X prime, the rate of change of X, they told us was 1/2. And they want us to find the rate of change of Y. Okay. So I've written down all my information, I've labeled everything and so forth. Okay, next step, write an equation that relates those variables. So here's all the stuff I have and the stuff I need. It's got X's and Y's and X primes and Y primes. So I need an equation that relates those. Any ideas? Really easy. X squared plus Y squared equals 36. That's it, right? Now that's going to change from problem to problem. It might be a Pythagorean theorem. It might be a SOHCAHTOA with sine and cosine. It might be an area of a circle. It might be, I don't know. If it was the balloon problem, right, we said R would be changing. The volume would be changing. It might be volume of a sphere might be our equation. If we wanted to know how, it could be a lot of different things. Okay, depends on the problem. All right, but there's my equation. All right, now what do you think I'm going to do? Remember what we're trying to find. Now, some people, very common, that's what the other class said too. They said solve for Y. We could, but it's a lot of unnecessary work, actually. Do the derivative. How do you do the derivative of something that looks like that? Implicit differentiation, because we're doing the derivative with respect to, look at our derivatives up there, dx dt, dy dt, we're doing the derivative with respect to t, time. And we don't care that it's not solved for Y, right? Now, in optimization, we wanted to get it in terms of one variable, right? We wanted R equals. We wanted P equals profit. We're doing max profit, area, volume. So we needed a V equation, an A equation. That's not true in these. Now, remember, I did show you that one kind of alternate way with implicit differentiation. I said, don't do that with optimization. With these problems, it absolutely is going to be implicit differentiation every single time. You're going to write your equation, and usually you're not going to do much with it, like solve it for something or anything like that. You're just going to go implicit differentiation with respect to t right after that. Okay, so let's do it. So what's the derivative of x squared? All right, I didn't hear a lot of people saying x prime. Why are we saying x prime? Because it's with respect to t. If we were doing the derivative with respect to x, then it would just be 2x. But it is not with respect to x. It's with respect to t. So it's 2x x prime, or 2x dx dt. Okay? That's why we have this dx dt right here. Right? Plus 2y prime. Now we're used to that, right? We're used to tacking on that y prime. We have to tack on x prime. Listen, we're going to be doing a problem here in a minute with volume of a cone. It's going to have r's and h's in it. We're going to have r primes and h primes. Right? We're going to have all those because they're all with respect to t. Every one of these, because they all have something to do with time. Something changing in terms of time. All right, and on this side? 0. Okay, now, what are we trying to find here? Y prime. Now, science teachers always like you to solve this now for y prime, right? They like to get the y prime by itself now and then plug your numbers in. I think solving with numbers is easier than with letters, so I would say go ahead and plug your numbers in now. It doesn't matter to me. You can do it at any time. Okay? But right now, I think we can start plugging stuff in. So right here we need x. We look up here, oh wait, I don't have x. Well, let's hold off for that a minute. What do I got for x prime? 1/2. Okay? What do I got for y? 5. What do I got for y prime? Oh, but we're going to get it, right? That's what we're going to solve for, is the y prime. Okay? So we're going to solve for y prime. But now I need something for x. No? No? No, you can't do the antiderivative of this, go from x prime to x, because that's with respect to t, not x, okay? So, Tim,
Plug the 5, the y equals 5 into y squared.
okay? We got an equation right here that relates x and y. Now is when Natalia had said earlier, she said something about the 5. Now is when we take our 5 and we put it in there. Now is when we put it in. But see, if we'd have left this a 5 right here, when we'd have wrote this equation, we'd have had 5 squared plus x squared equals this, and we wouldn't have had our y in there. We wouldn't have had our 2y y prime, right? If we'd have put our 5 in right away, we never would have had a y prime here. So when we plug that in is very important. It doesn't come until after we've done the derivative. Because y is a changing value. Only those values that are constant throughout the whole problem can I put in originally. Okay, now, so what Tim said is exactly right. So I'm going to go ahead and I'm going to put the 5 in now for y. So when y is a 5, so when the ladder has gotten down to that point where y is 5, what is x? How far out is the ladder? Well, what would you get? Square root 11. Okay, square root 11 would go right in there. And now we got to solve that for y prime. So the 2 and the 1/2 would just be square root 11 plus 10y prime equals 0. Now you could do some of this on your calculator. It's pretty simple, actually. You wouldn't really need your calculator, probably, other than to maybe turn it into a decimal. I mean, if this was the quiz, you could leave this square root 11 over 10. What would the units be? Meters per second, because this is y prime, right? And y was in meters, so y prime would be meters per second. Somebody give me a decimal on that. Somebody get their calculator out and just divide that real quick. Are we surprised it was negative? No, we said it should be negative because y is decreasing, so y prime should be negative. So negative point 3 something. 332 meters per second. If we go back to the problem, I think they've got that for us. Yes, negative 0.332 meters per second. That's how fast that's how fast the ladder's falling down. So when the ladder's going out at 0.5 meters per second, when the top is right here, it's dropping at 0.33 meters per second. Now, if we did it at y equals 3, we'd get a different answer. And y equals 1, we'd get a different answer. Okay? All right, there's all kinds of different examples. Here's an example of a boat. We're reeling in a boat. Okay? What's changing? This is not changing, so we go ahead and put a 20 here. But this is changing and this is changing. So we call that R and X. Now, when the rope is 45 feet out, we would put that in later. The 45 in for X later. Okay? And the rope's coming in at 2 feet per second. So what would that be labeled? The rope's coming in at 2 feet per second. In our picture, what would that be labeled? The rope is coming in at 2 feet per second. So that's this. That'd be R prime. And would it be 2 or negative 2? Be negative 2 because R is getting shorter. R is decreasing, so R prime is negative. So when you plug it in, you've got to plug in a negative 2. It's going to mess up the equation. It's going to mess up your answer if you don't. Okay, one of your homework problems is like this. You got this guy walking. Okay? You got a lamp post, and he's walking. Now, what things are changing? The length of his shadow. The speed that he's walking. Right? This green length is changing. That's the speed he's walking. What about the red dot? That's different than the length of his shadow. No. What would the speed of the red dot be? There'd be a rate that the black is increasing. That would be the length of shadow, the rate his shadow is lengthening. No. Well, I was thinking X would be the green. I would call this X. How far he is from the lamppost. And that's changing. So that's X prime. That'd be the rate he's walking. Let's call this S, the length of his shadow. That's lengthening, right? You've done that before, right? Seen your shadow get longer and longer. So let's call that S. That'd be like S prime. What would be the rate that the red dot's moving? Wouldn't that be the two together? Because the red dot is growing because his shadow's growing, but also because he's walking. So as he's walking, the red dot's moving, and the red dot's moving because his shadow is lengthening. So that would be those two rates added together. Now, we wouldn't use a Pythagorean theorem in this problem. In this problem, we would have similar triangles. You guys see the similar triangles there? If this was X, his length, the green is his length, and if this was S, the shadow, I can't put numbers there because those are changing quantities. What would be the equation that would relate these similar triangles here? No. See, I'm saying it wouldn't be a Pythagorean theorem because, yeah, this squared plus this squared would be this hypotenuse squared, but I didn't even label the hypotenuse because I don't want to know anything about the hypotenuse. I'm talking about similar triangles. What did you guys learn in geometry about similar triangles? Okay, wait, stop. Natalia, say that again. 6 over 15 is equal to S over, right? The corresponding sides are proportional. So this side to this side, those corresponding sides are proportional to this side to this whole side here. Now we could cross multiply, and that would give us an equation that would have S and X in it, right? Which we could then do the derivative, which would give us S prime and X prime, right? And we'd be able to find those lengths. Does that make sense? So there are various techniques you learned in prior math courses that you will have to use to set up these equations. You have to relate the variables in the problem. We have S and X in here. Somehow we have to relate those. I didn't want to do a Pythagorean theorem because that would give me extra stuff. All right? Now, let's take a look at, maybe you could put this in your notes here if you want. Well, let's don't do it yet. Let me just put this up here, and I'll put it up again that you can copy down if you need to. So basically it was steps 1 and 2 kind of go together. Draw and label a diagram and identify the various things that are in the problem. So like in this last problem we had X prime was a half. And we were trying to find Y prime. And they told us Y was 5. And, you know, the ladder was 6. And so we put that in our picture, right? Those things that are constant, you can draw in your picture and they stay constant. You can put those in your equation. But if they're not constant, if they're changing throughout the problem, you have to put variables there. Okay, step 3 is you write an equation. Now, our first problem was Pythagorean theorem. Our second problem there was similar triangle. So that we did a similar triangle and set up a proportion to write our equation. The next step, step 4, is to differentiate both sides with respect to t. That means do the derivative with respect to t. So you get X primes and Y primes and S primes and R primes and H primes, whatever the case may be. Now, hopefully, once you get all those, you've got numbers to plug in for those. So in step 5, you substitute the values you're given in the problem, and you solve for what they were asking for. And then the last step, of course, is make sure you got the right sign. In that problem we had, Y prime was negative. It should be negative, because Y was decreasing, so our answer should be negative. Okay? If Y is decreasing, Y prime's got to be positive. Okay. I'll put that back up here in a minute, but we're going to do this problem right here now. Okay? This is called a conical tank. Conical meaning cone shape. Okay? We got a conical tank. Water is flowing into the cone, and this cone, by the way, has a height of 16. So this height right here is 16, and this radius here is 4. Okay? So water is flowing into this cone at 2 cubic centimeters per minute. Okay, so that's going to be important information. How fast, and how fast is the water level rising when it is 15 centimeters deep? Okay, so now they've helped us out. They've drawn a picture for us. Okay, so you might draw this yourself on your paper. I would say draw yourself a quick little cone and the water. Draw the water in there. And H is the height of the water, and R is the radius of the water. Now the radius of the cone is 4, and the height of the cone is 16, but not of the water. Only if it's full would the water have that height and radius, right? Okay, and so I'll circle the 15, so that's important information too. All right, so we've drawn our picture. Now we're supposed to label or write down the given information. Right? So, what would we label the 2? 2 cubic centimeters per minute. What would we label that? Okay, let's back up. Let's do an easy one. Let's do 15. What would we label 15? H. Yeah, not Y. I don't have Y in the problem. I got R and H. I could have used Y if I wanted to, but we have H there. So would that be H or R? What is it?
H.
H. H is how deep the water is. So H is 15. Now is that changing throughout the problem?
Yes.
Can I put a 15 right there for H? No. That's changed. So I got to put an H there. But up here I can write H equals 15. Later I'm going to put a 15 in for H. Later. Okay. Is there anything that stays constant in this problem when it comes to the water? As the water fills up, right? So R and H are both changing, right? Okay. So what about that 2? What can I label the 2? Say that again. Sorta. We're getting closer. Would it be V prime? Yeah, big hint is the cubic centimeters. Cubic centimeters. Water is flowing in at 2 cubic centimeters per minute. That's volume. So that is V prime. Or dV dt. Right? Same thing. Now is that a positive 2 or a negative 2? Positive 2 because the volume is increasing. Now we just as easily could have had a tank with water draining out, like a water jug, right? We could have had water going out at 2 cubic centimeters per minute. Then it would have been negative 2, right? The volume is decreasing, so V prime would be negative. Okay, so V prime is going to be 2. We're going to plug that in later. Do we have anything else? I don't think so. Oh yeah, well, and what are we trying to find? We're trying to find H prime. dH dt, right? We're trying to find how fast the water level's rising. So that's the change in H. Okay? All right. So now, the third step was write an equation that relates these quantities. So we needed an equation that's going to relate V and H. What would that be? But the volume of a cone, right? Now, I will tell you that. I will give you that. Now, we'll do enough of these probably before the quiz that you should know it, but I'll probably put it on there anyway. The volume of a cone is 1/3 pi r squared h. Okay, it's just a cylinder divided by 3 is all a cone is. Cylinder divided by 3. What was step 4? Do the derivative with respect to t. Now, just thinking ahead here a minute. What is it going to look like, sort of, kind of, without actually doing it? Here you'll get V prime, which will be fine. That'll be a place to plug our 2, right? That'd be good. And what about over here? Well, okay. Rather than saying, won't there be like a 2, and then this is going to have to hang out there, right? And then won't there be like an R and an R prime? But won't there be an H prime too? See, can I plug the 15 in right now? No, that comes later. That can't come until, see, if I put a 15 in right now, I'm saying it's just constant. Then I won't ever, if I put 15 in right now, I won't have an H anymore, and how will I get an H prime? If I don't have an H, I can't get an H prime, right? So I can't put the 15 in there. And did anybody think product rule? Because if you're not thinking product rule, you're thinking wrong. You'd have to do product rule here. This is R squared, which is a changing amount, times H, which is a changing amount. This would have to be a product rule. So when we do this derivative, it's going to be kind of long over here, and it's going to have R, and it's going to have R prime in it, it's going to have H, and it's going to have H prime. Do I have stuff to plug into all those?
Yes.
Not all.
Do I have anything to plug in for R?
No.
No, and I certainly can't plug 4 in for R because that's the radius of the cone, not the radius of the Y. Okay? So that's going to give me too much stuff. Now, we've already looked at 2 examples where that wasn't an issue. Okay, we looked at the spotlight problem that had X and S in it. We had an equation. We had X prime and S prime, and we knew X prime. We're going to do S prime. We just did an X and a Y problem. That we didn't know what X was, but if we did know Y, so as soon as we put Y in, we could get X, right? Because we knew it added up to 36. Is there anything here that if I plugged the 15 in could tell me what H was? If I knew the volume of the water, maybe, right? If I put a 15 in for H, could I figure out R? No, because I still don't know V, right? So I do have a problem. So every once in a while, you write your equation, and there's too many variables in there. Now remember, we don't have to get this down to 1 variable, right? We just need to get it down to enough variables that we have information for. So in the last problem, we had X squared and Y squared. That was no problem. We said, you don't have to solve for Y. No, that's no problem. Just do 2x, X prime, plus 2y, Y prime. And then we plug stuff in, and we got stuff. Okay? But here, I'm going to have this R in here and R prime, and I don't have anything for that. So we got to somehow get that R out of it. Yes?
Doesn't it also say over there H over R equals 4? So can
It-
you
it-
use that as a...
Normally that wouldn't be in the problem, but it came from this, right here. Again, look at these triangles right here, guys. Aren't these similar triangles? Okay, and what's that tell you? It tells you H over R, those corresponding parts, would be 16 over 4. So you cross multiply there, you get 4H equals 16R. Now the question is, do I want to solve this for H or solve it for R? R, because I'm trying to get rid of R, right? I don't want R to be in the problem because I don't have any information about R. So this is what I do. So I'm going to divide by 16 and I get 1/4 H. So that was the secret right there. I had to know that in this cone, think about it, as the water rises, they're going to stay in proportion. The radius is always going to be 1/4 of the height as the water rises. The radius will always be 1/4 of the height. So what that allows me to do is what? Right here for R, plug in 1/4 H. So this is going to be very helpful. So I'll have V equals 1/3 pi, what's 1/4 H squared? 1/16 H squared, right? And then times an H. And now I should keep simplifying. But before I do the derivative, let's keep simplifying because it will make the derivative easier. So what is that all? And it'd be 1 over 48, 3 times 16, right? Pi H cubed. There we go. Okay, so there's my volume equation. Now that's going to be good because now, number 1, I don't have to do a product rule. Number 2, I don't have any R's in there. I just have H's, which means I have H prime, which is what I want. So now I do the derivative with respect to t. So V prime, which would be dV dt, right? Doing the derivative with respect to t. And on this side, what do I do? Well, right, but I mean, no. 1/48 pi is just a number, but how do I do a derivative? Of H cubed. I bring the 3 down in front. So that's 1/16 pi. Those are just constants, so they stay out there. H squared H prime. There we go. We tack on the H prime, just like when we did implicit differentiation, right? We do the normal derivative, bring the 3 down in front, drop that to an H squared, tack on an H prime. It's implicit differentiation. Okay, and now, do I have stuff to plug in? Put a 2 right there. What do I put in for H? 15. And then H prime is what I'm trying to find. Now, go to your calculator and do a solve if you want. I mean, it's probably easy enough. You can move stuff around for a little while and then go to your calculator or whatever. Or you can just go to a solve right now. But in your calculator, you wouldn't put H prime on it. You put X or H or whatever you want to call it. But and somebody give me a decimal. Okay, it's 0.045. 0.045 what? Well, units. 0.045 height. Centimeter. Now, per minute. Now I know in physics class a lot of times they want you to keep your units in the problem, right? You got to write your units as you go through the problem, make sure your units come out right. I'm not going to make you do that. You have to have your final units right in centimeters per minute, but think about what this was right here. 2 was in what? Centimeters cubed per minute. What was 15? Centimeters, and then we squared it, and then we divided it over. So you had centimeters cubed over here, and you divided by centimeters squared. So it should have been centimeters, right? So the answer should be centimeters per minute, okay? 0.045. All right? So, again, look at those steps. The same thing we had up there a minute ago. We said draw and label a diagram. So we had this cone-shaped tank. The water was rising up. We didn't know the height of the water. We didn't know the radius of the water. So we put those 2 labels in there. We called them R and H. They were changing. There wasn't anything really staying constant in those as the water moved. Okay? Then they told us this information about the height and radius of the cone. That helped us. We knew that R was always going to be 1/4 H. They told us it was going in at 2 cubic centimeters per minute. That's volume, so we knew we would call that V prime because it was a rate. Anything that's something per minute or per second, that's a rate. That's going to be a prime. Okay? When the water was 15 deep, that's when H is 15. So those were numbers we held and said we're going to put those in later. So we said, okay, now I need an equation that's got V and H in it. Well, that's the volume of a cone. So I would have given you that equation. There it is. We realized that we had R that we didn't really have information about, so we used this other information, which we didn't have to do in our other 2 problems. So I made this one a little harder. Okay, we had to bring that information in, substitute it in to simplify down our equation. Then we do the derivative with respect to t, which is implicit differentiation. So we have to think we're going to have h primes, r primes, x primes, y primes, all that stuff in these problems. Then once we do that, then we can bring that other information in to plug in to find our missing thing and then answer the question. Okay? So I'll put those things back up there. That is related rates. Notice they're going to just be very different kinds of problems from max-min problems. Max-min problems are find the max profit, find the largest area, find the minimum cost, right? They're just going to sound different than a problem that says, how fast is this changing? How fast is this increasing? Okay? Those are rate problems, and so they have a whole different approach. I mean, there are similarities, obviously, but they're doing different things. Okay, so I'll put that back up in case there's some more of that you wanted to get. All right, the homework then is 2 of these kind of questions. So if you want to try to get started on them real quick here before we go. But in section 4.5, number 4 and number 7. Okay, one is this shadow, and it refers to example 3, the person walking with a lamppost and their shadow, right? And it's worked out for you in example 3. They change a couple of numbers, and you do that in number 4. Number 7 talks about the example I was giving where like you click and drag with a mouse and you have a rectangle where the length and width are both changing and the area. Okay, so it's that kind of thing. So draw a picture and try to mimic this process. And we'll talk some more about it tomorrow, do another example, maybe have some work done. Okay, and then in the business packet, do all of them. That is, all of the ones that are circled. Okay, so 3 and 8 was supposed to be part of your assignment for today, so you just have to add that on to tomorrow. So in the business packet,